Assalamualaikum and hi everyone. This is a pre-recorded video 20 for chemical bonding. In the previous video, we have been introduced to molecular orbital theory. This video is the continuation of MOT from the previous video. Let's continue. This picture shows the difference in a level of energy for group 1 to 5a and 6 to 8a in periodic table. The sigma 2s and 2p molecular orbitals interact with each other so as to lower the energy of the sigma 2s MO and raise the energy of the sigma 2p MO. So you can see the difference between these two groups. So these are from the group 1 to 5a, and these are from group 6 to 8a. Oh yes, you can check the answer of the exercise in the previous video here, but please remember to write the correct electronic configuration, especially for different groups of elements as shown in the green and red circle here. So this is group 1 to 5, and then this is group 6 to 8. There's a difference here. Okay, so for group 1 to 5, pi 2p and pi 2p, py and pz here actually lower energy compared to sigma 2p. But for oxygen here, which is group 6, so sigma 2p is lower than compared to pi 2py and pi 2pz. So the arrangements of electrons follows. Okay, so for lithium, beryllium, and so on until Ne2. One of the advantages of MOT is this theory can be used to determine the bond order that indicates the bond strength, which is larger bond order means greater bond strength. And also MOT can indicate the number of bonds that exist between two atoms. Other than that, MOT can be used to know that whether a molecule or ions exist or not. The formula to determine bond order is half times the number of electrons in bonding MOs minus the number of electrons in anti-bonding MOs. Okay, you have to remember this formula. Okay, so this is how we determine the bond order. Take an example for He2. Okay, so He2 in here. Okay, so I will take one example. Sorry. Okay, so this one. Right, so number of electron in bonding is 2 minus number 2 electron in anti-bonding. So divide by 2, which is 0. So what does this mean? Okay, so 0 is the answer for He2. And then the answer for H2 plus is half, H2 is 1, okay, and then H2E2 plus is half. So this is the meaning of the number that we get when we determine the bond order. Bond order is 0, suggests that the molecule doesn't exist, meaning that He2 not exists because the bonds are unstable. And when bond order is greater than 0, suggests a stable molecule. A fractional bond order suggests that the bond is relatively unstable compared to a whole number. We are still on the bond order, and there are definite correlation between bond order, bond energy, and bond length. As the bond order increases, the bond energy also increases, and the bond length decreases. Okay, we have learned this in our previous video about the bond length and bond energy. Large bond energy associated with N2 molecule, which the MOT model predicts will have a bond order of 3, which is a triple bond. Please do this exercise and discuss the answer with your lecturer. In the previous video, do you still remember the question about why water is paramagnetic? MOT can be used to determine the magnetic properties of a molecule. By definition, paramagnetism causes substance to be attracted into a magnetic field, which is associated with unpaired electrons. Those compounds with unpaired electrons basically have paramagnetism properties. And dimagnetism causes substance to be repelled from the magnetic field, and then this is associated with the paired electron. Okay, so it's opposite to each other. Let's do this exercise and discuss the answer with your lecturer. These are the pros and cons of MOT. The pros are MOT can be used to predict magnetic property of a molecule, which should be paramagnet or dimagnet, and MOT can be used to determine the bond order, can determine the bond stability. Molecules that have bond order equal to 0 doesn't exist. But it has some drawbacks or disadvantage. The MOT is limited to diatomic molecule, for example Li2, B2, O2, N2, okay? Molecules that have only two atoms bonded together. We are actually towards the end of this chapter. So this is a bit of information about sketching a molecule, because molecules are three-dimensional objects. Our drawing should indicate their three-dimensional quality. And how to do that? By convention, a field wedge indicates that the attached atom is coming out of the paper towards you. Okay, so field wedge, you have to remember that. Okay, this one, field wedge. A dash wedge indicates that the attached atoms actually is going behind the paper away from you. All right, so for example here, as you can see here, you may draw a molecule like this. Okay, this is a normal one. However, this is not showing a 3D molecule. That 3D molecule should look like this one. However, to represent the 3D molecule, you can use a molecule structure or sketching like this. Okay, so this field wedge actually represents the atom fluorine actually coming towards you, and the dash wedge here, okay, meaning that this fluorine atom behind the paper. Okay, so these other two fluorines here and here is in the paper plane. I would like to sum up the chapter with 7 points. First, the VSEPR method is used to predict the shapes of molecule and polyatomic ions. Second, if all electron groups are bonding groups, the molecular geometry is the same as the electron group geometry or electron domain geometry. Third, in the valence bond theory or VBT, a covalent bond is formed by the overlapping of orbitals of the bonded atoms in a region between the atomic nuclei. 4. Hybridized orbitals include sp, sp2, sp3, sp3d, and sp3d2. Fifth, unhybridized p orbitals overlap in a side-by-side fashion to form pi bonds. 6. Single bonds are all hybridized sigma bonds. Double bonds have one sigma bond and one pi bond, and triple bonds have one sigma bond and two pi bonds. 7. In molecular orbital theory, atomic orbitals of separated atoms are combined into MO or molecular orbitals. So we finally covered all subtopics in chapter 3, from basic concept, ionic bond, covalent bond, resonance structures, formal charges, intermolecular forces, metallic bond, VBT, VSEPR, hybrid orbital theory, and molecular orbital theory. It's a long chapter, but I hope you guys get some benefit from this video. If you guys have any problems or misconception, please refer to your lecturer and ask more explanation. Thank you, and see you guys in chapter 4.